Hello, I am Subhi Barg. I am an assistant professor at Mid-Sweden University. In a recent video that I have uploaded on LinkedIn and on my YouTube channel, I have shown the uniqueness of the air gap solution. The uploaded video is about the existing expressions and formulas used to calculate the air gap. In that video, I have shown that these formulas are wrong. Of course, Professor Binyakov, he did not agree with my formula and he said that it is wrong. In this presentation, I will demonstrate the uniqueness of the air gap formula that I have developed, and also I will answer to Professor Binyakov comments. So let's start by demonstrating the unique air gap formula. So the energy that you will convert from its electric form to its magnetic form, it can be expressed by the following equation. So the energy, it is the ratio between the power and the frequency. The power, it is the integral over one period of the voltage and the current across the inductor. We divide by the frequency to get the energy. This electric form or this quantity, it can be also expressed as function of or in its magnetic form. Using the principle of conservation of energy, we can equate both, and the magnetic form, it is expressed as function of the reluctance times the flux. Of course, the flux is the product of the cross-section multiplied by the magnetic flux density. If we combine both expression, we can get also the expression that is function of the inductance and the current square, which is in between. That expression, it is a combination of the electric and the magnetic form. The one to the left, it is the electric form. The one to the right it is the magnetic form. The one in the middle, it is a combination of both. It includes the magnetic variables and also the electric variables. So here to understand the energy that will be stored in the inductor. So now we can express the integral of the voltage and the current as function of their RMS value. That is quite easy for a student or engineering student to understand. It is possible to write that one. And the second term, or the magnetic term, as I have explained it, we can, the reluctance, the equation or the expression of the reluctance, it includes also the variable, the cross-section variable. So we can simplify by A in both, and we get this term. So this term, if you multiply by the cross-section, it means the volume of the core and the volume of the air gap, or the volume of your gap. So here this term, for high permeability material, it is negligible, and the full energy it will be stored in the gap. That's well known for most of people who work on the design of magnetics. Now we can use Faraday's law to replace the voltage. So here the voltage, or the RMS value of your voltage, can be expressed as function of these variables: the number of turns, the cross-section, the frequency, and the magnetic flux density. This is Faraday's law also. So we cannot argue in this law. So it is clear now. It is start to be clear for all that we can simplify by the frequency first. So they will be cancelled out, and also we can simplify by the cross-section here in the first term, the electric term, and the magnetic term also. So here the cross-section, the frequency, they will be cancelled out, and what is remaining now, so we can derive the expression of the air gap, and you will get this expression here. It is only function of the number of turns, the current, which is the RMS current, but also it can be expressed as function of the DC current multiplied by some factor, and divided by the magnetic flux density minus this term, which is negligible for ferrite material. For low permeability materials, you need to consider this term. It's not negligible. In my previous video, I have shown the limit between, the limit, or when you design, you calculate the air gap for different number of turns and the given current. I have shown the limit between the high permeability material and the low permeability material. So you can see this video on my YouTube channel. It's very important one to understand how to select your magnetic material. It's also very important when you do optimization, because in the optimization you have to consider the core loss, and the core loss, it depends on the magnetic material. It's not the same like you design an inductor with ferrite or an inductor with powder or any other materials. That's very important and step to have to consider that limit. So now I have finished with the demonstration of the unique air gap formula, and now I will move to comment or to analyze the answer of Professor Benyakov. So here it is the comment of Professor Benyakov. It is posted in his page on LinkedIn, and we can read his answer. So it is copied as it is. Dr. Subhi Barak, for a given L and I, N is function of the cross-section area of the core. So you are trying to trick us by hiding A in N. Clearly, LG is function of the area. This is trivial because for a given B, the volume of the gap, the volume is equal to LG times the cross-section is proportional to the stored energy given by this equation. So if A increased, LG needs to be decreased. This is the comment of Professor Benyakov. It has two main parts. The first part is related to the dependence or the relationship between the cross-section and the number of turns. And the second part, it is related to the energy and the air gap and the cross-section. So here I will not discuss the first part because it is it's not important and it's more difficult to explain in this video later on. But when I explain the second part, you will understand the dependency between N and A. But just to summarize this, A and N, they are dependent on each other just from point or the side of Faraday's law. That's it. So the second part, he said, for a given B, so a constant energy, if we increase A, LG needs to be decreased. So here it is at what I have understood from his comment that if we increase A by a factor of X, LG needs to be decreased by the same factor. So this is clearly, from his statement, because he said that, B, it is, for a given B. So it is for a given B. So the energy is constant. The energy density is constant. So now let's start to explain his comment. So here, just to repeat, if we increase A by X, the air gap needs to be decreased. So how we can understand this? So we need to look to the impact of these changes on the inductance, because the inductance, it will impose the energy, and it will see that the energy, it will change. So the inductance of the inductor, the original inductor, it is expressed as function of the reluctance model. It is function of the permeability, the number of turns square proportional to the cross section and inversely proportional to the air gap. So here, as we said, we can neglect the first term in the denominator. I'll see here the core length, and it can be only expressed as function of this one. So now if we increase A by X and reduce also the air gap by X, so what we will get now, after we make the simplification by LC here, we cancel this term. So we will get that the new inductance of your new core that you have changed, you have increased A by X and reduce it the air gap by X, you will get the inductance. It is changing now. It is times the original inductance multiplied by X squared, and this X is the change of in A and on X. What does it mean this? So let's see its effect on the current ripple or the current in the inductance. So the current can be determined from Faraday's law always. Voltage is equals to L times delta I with respect di with respect to time. So you can divide delta I here for X. It is the voltage across the inductor, which is constant there, divided by L naught times X squared. So it is equal to the original ripple divided by X squared. That's very easy. Now let's see the impact on the energy. So the energy, which is function of Li squared, that's a fundamental law to calculate the energy in the inductor. So the new energy that you will get, it is Lx, L sub x multiplied by delta I sub x squared. So it is equal to the energy, the original energy, divided by x squared. So you can see here that the energy, it is reduced by x squared, but the air gap, you have only decreased by x squared. So let's understand this what's happening now. So at the beginning of this this presentation on the previous slide, we have said that the gap, it is used to store the energy for ferrite material. 99% of the energy will be stored in the gap. So now the energy has decreased by x squared, but the gap has decreased by x. What does it mean this? It means that the gap is oversized. Because if the energy has decreases by x squared, the gap also should be decreased by x squared. Because the gap, it is the tank where you are storing your energy. So you have decreased the gap by x, but the energy that we get here, it is decreased by x squared. So the tank or the volume of your tank, which is the gap, you have increased A by X and you have decreased the gap by X. So the tank volume has not changed, but the energy that we get here, it is reduced by X squared. That's what we called the fake inductor. So you have a big tank to store lower energy. This is clearly wrong way to design your inductor. So you can see my explanation of the fake inductor or the wrong designed inductor that is used nowadays by manufacturers, where they only change the air gap to change the inductance. You have the same core volume, the same number of turns in most of the cases, and they are trying to change the air gap to change the inductance. So the relationship between the air gap and the inductance, it is non-linear. The same thing to the energy, it is non-linear. So you cannot just increase the air gap. That's it. That's completely wrong. You are oversizing your air gap and you are killing your inductance. This is explained also by Professor Chuk. So you can visit his page on LinkedIn, and he write a lot of report on this. So the conclusion here, what you have to remember always, there is only one unique solution for the air gap. There is only one unique value of the gap for a given number of turns and the current and a B and the core volume. That's the conclusion that you have always to remind in the design of your inductor. Thank you very much for your attention. I hope that you find this useful, and also, as always, feedback and comments on this video or in this presentation are very welcome. Thank you very much.